You heard all about catastrophism and the geological evidence for ancient and large amounts of water in the ancient past scoring the landscape across North America. And no matter how many times I hear Randall talk about these issues, every time I come away with new information. I come away with a deeper and frankly, a more concerned perspective on the effects the forces of nature can have. If you look at the erratics, and Randall, we've talked about those erratics. Those are still one of my favorite topics, massive boulders, and how we can literally piece together puzzle pieces about how maybe 12,800 years ago or so, stone boulders that massive could be moved and what kind of forces it would take to do that. But today we are going to go in a slightly different direction, because with catastrophism in mind and having looked to the past to try and learn about what happened in the ancient past and what could potentially happen again one day and what kinds of forces can act on us. Please, I do want to remind you, you want to silence your phones for the showing this afternoon. Silence those smartphones, folks. Thank you. People who would have come in the ages after a cataclysmic event or whatever kind of an event that, again, there is a growing amount of evidence in support of scientifically regarding the Younger Dryas period some 12,800 years ago, the people who would come in successive generations after that, who are advancing, rebuilding, growing, learning, new advancements in architecture, advancements that would lead to the rise of agriculture, monolithic monumental sites like Göbekli Tepe and others, Karahan Tepe that we heard from Hugh Newman about. When you look at the structures and the way that they were built, it's hard to look at these and say there wasn't mathematics, that there wasn't a tremendous amount of knowledge that ancient people had. And so today, for this special master class, and from a master teacher, I think we're going to get a really unique perspective on all this from Randall Carlson. So please welcome again Randall Carlson, Sacred Geometry. Randall, you want me to move this mic stand over here for you?
Sure.
Okay.
I think I am
You got
okay. Whatever you think. You're the professional there, Micah.
Turn it over to you, sir. Go ahead.
Well, greetings. So, we're going to, let's see. Can you actually, look at there. So what are you seeing? Are you seeing my hand moving here? Oh, okay. Would it be possible, Beckett or tech person, possibly to shift this around just a little bit to try to get more of a direct, this will work, but if we can get a little bit more directly over it, it'll be better. Is that possible? It is potentially possible. Okay. While he's doing that, I am going to... Yeah, a little more perpendicular to the paper. Okay. Yeah, that's better. Yes, absolutely, that's better. What do you think about a little couple of minutes of a percussion warm-up?
I think you'd get everybody fired up. I like it.
We like fired up.
Yeah. Does that work?
Yes, I think, no, that'll work. That's better. Thank you, Beckett. I take back some of those things I've been saying about you, Beckett. But not all of them. I thought we'd do a little percussion here because percussion is rhythm, and rhythm comes from the same root as the word arithmetic, and it means to flow, to flow. So, got to get, oh, that was nothing. That was nothing. That was just, we got to get warmed up. Normally it takes a good 15 minutes to get warmed up. So we might take a little break in the middle. And after we've learned some drawing. Anyways, okay. So everybody's got your paper and pencil ready to go? Okay, so step number one, let's see. Okay, if I twist this paper a little bit here, like this. Well, okay, so first step, and you've got your compasses, right? All right. You're going to have to take the little orange plastic off the end, put your pencil in the bulldog clip there, and what you're going to want to do, make sure that your wing nuts are fairly tight. You want to be able to move it, but you don't want it to be loose. And what you're looking for is an isosceles triangle, so that you don't want this. You don't want this like this. You don't want this. What you're looking for is to have from the pivot point down to the metal tip, and from the pivot here down to the pencil tip, you want that to be the same distance. Okay, so then what we're going to do is just learn how to use the compass first of all. Now when you're drawing, what you're working towards is just using thumb and index finger like this. And what's important here is that when you are drawing an arc or a circle, try to keep the fixed limb of the compass more or less perpendicular to the paper, and then you lean into the direction you're turning, and hopefully you can see this on the screen, and you try to do it in one movement like this. And if you have to, go ahead and stabilize your fixed limb like this, and it takes a little practice, and then go ahead and adjust your compass, and then make some concentric circles until you start getting the feel of the compass. And see, I'm also doing this. This is acceptable. And you're going to need to draw, typically when I do a sacred geometry retreat, we provide smaller compasses too, so you can get small diagrams. This is for really drawing larger arcs, so don't be afraid to draw large and fill up your paper. Now also normally I have several people who rotate around to assist. We don't have that here today, so you're kind of on your own. Yes. Can you see? I can't tell. I can't see the big screens. Are you able to see my drawing? Is it, because I could. Okay, let me try this. If I put a pen here. Oops, a little off, but okay, is that showing up better? If I use the pen, let's see. No, that's not. And here's a little trick too. If you hold your fixed limb in place, you can actually just rotate your paper as well. Let's see. Okay, now that outer circle I just drew, is that easier to see? This one? Let me see. Okay. Okay. Pardon me? I'm quite certain he had some kind of variation on a compass, yes. Now, when we want to switch over to the slideshow, you're out there and I can just signal you. Okay. Because I thought we. Okay. Now, one of the first things you need to learn how to do is how to set out two lines that are perpendicular to each other. So, if you watch what I do here, I'm going to draw a line. And you can see that fairly good, I think. Good. All right, so now what we want to do is I want you to draw a line like this, and then take your pencil or pen, whatever you're using, and just make a point somewhere around the center of that line. Now, when you're making a point, you're drawing, here's what you're going to do. Take your pencil like this, hold it perpendicular to the page, put down some pressure, and then rotate it like this. And what that'll do is it's going to make a little dimple. And then when you come back to your compass, you can actually find that little dimple with the metal tip of your compass, right? And you're going to find as we go through these exercises that that's going to be very helpful. Because typically what happens is that novices, and sometimes even supposed so-called experts like me, will, if you get a little bit off, if you're doing a drawing, and the more complex the drawing is, if you get a little bit off in the early steps, every step from there on multiplies. And then by the time you get to the end of it, you got a mess on your hands. So here now, in order to set out perpendicular lines, if you've done this so far, you've drawn a horizontal line somewhere around the middle. It doesn't have to be too precise. You've made a little dot there, a little indentation, like I'm doing here. Then what you're going to do is you're going to take your compass and you're going to put the metal tip in that little point, and then you're going to mark off on both sides of that line. If you can see what I've done here, if it's not too small. So you've got a central point, and then you've got 2 points equidistant. So far, so easy, I think. I'll try to do this so you can see again. In fact, I'll make this a little bigger than, I'm going to make it bigger on my page than you need to. Just so you can see it. So I've got, and you know what? I think we'll call, sometimes it helps to name these, and we usually just name them using capital letters. So we'll make this intersection over here on the left A, and over here on the right will be B. Okay, so now what you're going to do is you're going to put your compass metal tip at A and open your compass to AB. And then you're going to draw an arc up, and you're going to draw that arc just long enough so that it goes a little bit further than a perpendicular. I want you to visualize a perpendicular line from that dot that you drew. See, I think you can see what I've done here. Hopefully you can see this coming up this way. Then you're going to come over to B, and you're going to draw another arc until the two arcs intersect right here, like at the top. And then once that's done, you're going to take your straight edge, and here's the best way to work your straight edge, is that you're going to take your pencil, and where the two arcs intersect, carefully put, oh, thank you, that should, yeah. Put your pencil on, eyeball it as close as you can, put your pencil on that point where the two arcs intersect. Bring your ruler, I'm trying to get here so you can see where I'm not blocking. So this, you bring your ruler up to your pencil, and then you pivot it until it lines up exactly with the dot that you put on your paper, on your line. And I'm going to, let's see how this works. Ooh. And if you do that, it should be more or less perpendicular. Is it working? Or are we stuck? So the first thing, draw your line, establish a point around the center of that line. Use that point as the center from which you're going to swing two arcs that are going to be the same length on either side of your line. I'm calling the one on the left A and the one on the right B, and then you're going to use those as centers, and then you're going to draw two arcs that will intersect. If you can see what I've done here, they intersect there, and where they intersect, if you've done this carefully, your A and the B, where they intersect, that point, going back to your original point, which I think I will call C for center, right? And we'll call this point up here D. So that should be perpendicular. Now, even if you're drawing something that doesn't have perpendicular lines in it, it's still an extremely important step to be able to know how to set out perpendiculars. Now, I'm going to flip my paper around, and we're going to do a second case. So this is one of the Euclidean propositions right here. To erect a perpendicular line, to erect a perpendicular line to a given line through a given point. That's what we just did. Now we're going to draw a perpendicular to a given line through a point that's not on the line. So let's just say we start out and we've got, use this again, we'll make a horizontal line, and then we'll make a point that's not on the line. Can you see that right there? So what you want to do now is you want to be able to draw a perpendicular to the given line, and we'll call that, we'll just call that the given line for now. So what you do is you, and I would be using my pencil otherwise, but for the sake of you being able to see what I'm doing. So now I'm going to call this point C. Just call it, this dot up here will be point C. Now place your compass, metal tip, compass tip on C, open up, and you're going to draw an arc that will intersect your given line in two places, like this. And we'll name those points. We'll name them A and B. All right, so the next thing I'm going to do is I'm going to use both A and B. You're going to, as you get familiar with these kinds of drawings, you're going to begin to see the logic of it, where each step will give you the points and the lines that you need for the next step. So here now we've defined A and B, and I'm going to use those, and watch carefully. I'm going to just open my compass to more than halfway. More than halfway, right? So this is getting a little in the way down here. Let's ignore that. I'm going to draw an arc like this. Then I'm going to go over to A without changing my compass, and I'm going to draw another arc. Hopefully you can see what I just did here. And we'll call that point D. So that's point D right there. And for the final step, you'll take your straight edge and use the same technique. Take your pencil, and it doesn't matter, you can use C or D. Put your pencil right there, right? And then you're going to move your straight edge up to it until it contacts, and then you're going to pivot around and line up as close as you can with D, and then you're going to draw a line, and that'll be perpendicular. How did I get D? Okay, watch, careful. So I'm using A and B. So I kind of randomly opened my compass. It just needed to be more than halfway. And then I'm using below, I'm kind of crammed here because I normally use a much bigger pad, but this is going to work fine. So I swing an arc using A as a center, and then without changing the compass, the radius of the compass, I then go over to B. I swing a second arc, and they will intersect right there, which will give me point D. Then my straight edge, say I'll move it up to D, and I'll pivot it around and line it up with C, and then I draw my perpendicular right there. Now, the interesting thing is that builders of old typically would use a knotted rope for increments. Sometime later it evolved into using a chain with very standardized size of links, right? So there was a chain called a Gunter chain that each link was an increment of 0.792 inches, right? So if you had 10 of them, it would be 7.92. If you had 100, it would be 79.2, and if you had 1,000, it would be 7,920. If you had 100 of them, it would be 792, and if you had 1,000 of them, if you had a chain, it was 1,000 links, it would be 7,920 links, which you're going to learn is a very interesting number because it's very close to the mean diameter of the Earth. And I think that there was definitely in the ancient systems of measurement knowledge of the size and shape of the Earth. And the term for the knowledge, the body of knowledge that describes the size and shape of the Earth is geodesy. Geodesy. That's the system of measuring the size and shape of the Earth, because you know the Earth is not perfectly spherical, right? You know that the Earth bulges around the equator, so it's called an oblate spheroid. The equatorial diameter is 26 miles greater than the polar diameter. And it's because of that bulge that the Earth, it helps to stabilize the Earth, because you know the Earth's axis is not completely fixed with respect to the stars. It's moving like this over a period of somewhat around 26,000 years, right? And that's going to be the result primarily of the gravitational attraction on the Earth's bulge, because the moon going around is trying to straighten the Earth up, in effect. That's kind of an oversimplification. That's basically what it's trying to do. But because of the momentum, the inertia of the Earth spinning around like this, it doesn't really ever straighten it up. It keeps it a tilt of about 23.5 degrees. Although that tilt is not steady, it's what, 22 and something and 24 and something, and that's part of some of the cycles that affect the climate of the Earth, actually, is the tilt of its axis. Okay, so anyways, it's interesting that if you were to take a sphere that was the same volume of the Earth, perfect sphere rather than an oblate spheroid, the diameter of that sphere would be just about 7,920 miles. It's also very, very close to the diameter of the Earth from the Tropic of Cancer to the Tropic of Capricorn. And you know, those are the points where when the sun is perpendicular, that's when you have the solstices. So right now, summer solstice, the sun is virtually perpendicular to the latitude 23.5 degrees north, the Tropic of Cancer. So it's a very interesting, intricate machine, and sacred geometry is one of the systems whereby you can gain insight into the workings and the functioning of the machine, and you end up with these repeated coincidence or synchronicities between the numbers that show up when you're working the geometric exercises, as are also found in the size and proportions of the solar system, and also in the timing of the orbits of the planets, particularly the Earth, but other planets as well. We won't have a chance, I don't think, to get into that level of the stuff today, but it's quite interesting when you do, and you find these synchronous reoccurrences over and over again. So now let's go, and I'm going to show you the third way. Say that again? Yes. 0.792 inches. I don't know. See, that's a suspicious word for me. But yeah, so in the way we know 7.792 is because if you had 1,000 links in the Gunter's chain, it would literally be 7,920 feet, or 792 feet, or 79.2, right? So that's a good question. Is it a coincidence? Well, as far as coincidence goes, if it was a singular example, I'd probably say, yeah, it's a coincidence. However, it's not a singular example, but there are many such examples, then maybe we might consider that it's not a coincidence. Yes? The what? Say one more time. Well, the number 9 will be showing up repeatedly. Yeah, and right. Okay, so now I'm going to show you a third way, because, so here was what I was going to get at, is that if you're out on a site, and like the builders of old are out on a site, and they're ready to build a magnificent cathedral or a temple, or even just a little, not much more than a hovel, really. What they would do is they would find the center first, and then they would work from there. So the first step would be to determine the center. In Greek, the term was omphalos. So when they were going to lay out a temple, they would find and omphalos meant navel center. And the idea was that the structure that they were about to build was going to grow organically from this center that was established. Typically, there would be a sensitive person who would come in and was able to map out the energy patterns in the landscape, and they would determine that there was a special spot within the building site. Like at Chartres Cathedral, for example, there was an ancient spring that was at the intersection of two fault lines, and that serves as a sacred center for the building of the cathedral. So first thing is you establish the sacred center, which is equivalent to us establishing a point on our paper. The next thing is to establish a line, and there were different ways of doing that. One way would be that if you have a vertical pole, and it was in the Greek it was called the gnomon pole, and I think that obelisks in ancient Egypt served the same purpose. They were in effect kind of like sundials. You put a vertical pole in, and let's say that, let's say it's summer solstice. Okay, so the sun rises in the northeast, and as it's rising, when it first breaks the horizon, is coming up. The shadow from that pole is going to be very long, isn't it? Well, as the sun is rising in the sky, the shadow is shrinking. Now, the sun is doing two things. It's rising, but it's also arcing over. So solar noon would be when the sun is standing due south, precisely south, right? Now, what's happening to the shadow as the sun is rising? Well, it's shrinking, but it's also moving, because as the sun is rising, the shadow is moving around. At noon, the sun will be due south, and the shadow will be pointing due north. Now, this is reverse it if you're, in the southern hemisphere. Now, the sun continues around. As it goes down, the shadow from the pole swings around. So it's doing two things. It's swinging around, and it's also growing in length. Now, so what the builders would do is they would establish their sacred center, and they would draw a circle around it. And they would determine that circle, depending on usually how big the structure was going to be. And then, picture an obelisk in your mind, or a pointed staff set in the ground, so that your shadow has a nice point on it, right? So now, as it's shrinking, while the sun is rising, there will come a point somewhere mid-morning where the point of that shadow precisely intersects that circle you've drawn on the ground. You drive a stake right there. Now, you come back in the afternoon, and you're going to see the exact reverse of that. As the sun is going down, then you're going to see that the shadow is swinging around, and it's also getting longer, because you draw that circle. At noon, the point of the shadow is going to be within the circle, right? As the sun is going down, the shadow is swinging around, almost like the hand of a clock, and it's getting longer. And then it's somewhere in the late afternoon, the shadow will get long enough. Just when the point of the shadow intersects the circle, you draw a second stake. Now, the next thing you do is you connect those. Like if I'm going to do a layout, I would then connect those 2 points with simply a mason's line, right? Well, it turns out that line is going to be almost precisely due east-west, right? So now you've gone from your point, which is the sacred center, to the line, which is going to give you an east-west axis. Then you basically take your chain or your knotted rope and duplicate what we just did on the paper, and now you have a perpendicular that's going to be north-south. So now you've established your 4 cardinal directions. And whether you're aligning your structure to the 4 cardinal directions or not is not as important as knowing where, the Great Pyramid of Cheops is aligned very accurately to the 4 cardinal directions. But you might not be using that. You might be wanting to align the axis of your temple, let's say, to the rising position of the Pleiades or the Dog Star, something like that. But your point, you've got to have this datum. You've got to have this reference. So you know the cardinal directions, and then you can adjust the axis of your building according to those 4 cardinal directions. And then if you bisect the right angles that you have, you now can get your ordinal points, like your northeast, southeast, southwest, and northwest. And typically, if you look at my business card, you'll see that I've got that compass on the business card. I don't know if you can, there it is, see. Now, I've used geometry to create that. Maybe we can even get far enough today that I'll show you how we draw that. But so, laying out perpendiculars. Now, there's one more case that I want you to see. It's a little more complicated, but this is if you're a given line and you've got an end point on that line. Now, let's say I'm laying out a building and there's a big rock there, or another building, or a cliff, or some nice trees that I don't want to destroy or whatever. You just saw that when I drew the line and I used the point on the line or the point not on the line, in either case, I had to have some room to move my compass, didn't I? Now, one of the things that I may run into, and I've actually run into this on building sites, is that you might you've got a line and you want to erect a perpendicular, not somewhere around the center, but to the end of that line, right? So that's what I'm going to show you how to do now. And with these 3 cases, you will now be able to erect perpendiculars in virtually any circumstance. Now, we'll draw some cool things like hexagons and octagons. We may draw a seven-sided, because the numbers, when you have numbers, the prime numbers like 7, for example, there's no way to geometrically draw a perfect heptagon. Somewhere in there, there's going to be a little fudge factor. Whereas like with a hexagon or an octagon or a decagon or a pentagon, you can draw with precision because the numbers work out exactly. But now normally when we do the sacred geometry retreats, I have everybody have a TI 30XA scientific calculator. And we can do some very cool stuff with that because to me, one whole dimension of this study is the numbers. And you asked about the number 9. Yeah, and then when you do a simple calculation, I'll say, okay, come up with the, what is the angle between two edges of a pentagon? Well, it's more than 90, isn't it? Right? Well, it turns out to be 108 degrees, 108. And then, of course, in a pentagon, there's 5 corners, so the total number of degrees that measure the pentagon is going to be 5 times 108, or 540. Now, you asked about the number 9. So if you resolve those numbers to a single digit, what do you get? 1 plus 0 plus 8 is 9. 5 plus 4 plus 0 is 9. Think about the number that we used for the diameter of the Earth, 7,920, right? 7,920, 7 plus 9 is 16, plus 2 is 18, 1 plus 8 is 9. So you're going to find that 9 is a repetitive number in this system over and over again. Yes? Okay, well, the plumb line is not necessarily going to be from the sun. This plumb line is going to be from the zenith, which is like if you had a flat level, like if you're at sea and you measure up 90 degrees from the horizon in every direction. So what's directly over your head, that's the zenith. So when you're hanging a plumb bob, if you think of it as a vector or an arrow, the upside is pointing to the zenith, the downside is pointing to the gravitational center of the Earth. So that gives you your vertical axis, and your pole that you put into the ground has to be vertical. Otherwise, the geometry doesn't work. So that's a good point. You do use a plumb line to, yeah, and if you look in a lot of the Egyptian iconography, you'll see a plumb line. You look in old Masonic manuscripts and stuff, and you'll see the plumb line. In fact, that's one of the major sacred tools of the ancient Freemasons was a plumb line. So now now this is where the going is going to really get tough. So what you're going to do is you're going to make a horizontal line. And then we'll put a dot, let's say, on the left end. And I'm making it big so that you can see it. And you know what? I really could use some water. All right. Make your line, your paper. I've made my line about maybe 5 inches, 6 inches. Oh, thank you. Perfect. Perfect. So we'll call this point A here on the end, right here. So our goal is to erect a perpendicular to this line, our given line, that goes through A, the end point. So to do this, I want you to, if you look up here, somewhere around the center of your line, and above that line, maybe if your line is 5 or 6 inches, you're going to want to go 2.5 inches roughly. It's kind of arbitrary, but within limits. You're going to put a point. And I'm putting my pencil there, and let's see, then I'm going to twirl it like that to make my nice little indentation. And I will call that point C. And I use the point C just to kind of remind you that this is going to be a center of an arc that we're going to draw. So does everybody have your given line, endpoint A, center C? So now I'm going to put my compass at C, like this. I'm going to carefully adjust the setting of my compass to CA, like this. And then I'm going to draw a circle. Oops, I just clipped the end. You want to be able to intersect your given line, and I'm drawing a circle here, like this. And if you miss, if your circle ends up outside your given line, just use your straight edge and make your given line a little bit longer. And where the given line intersects the circle, let's call that point B. So you draw your line, somewhat arbitrarily establish a point C. If you've drawn your line, like I said, 5 or 6 inches, make this 2, 3 inches, maybe let's say 2 inches above, somewhere within the middle third, say. And then your compass is going to go, your center is going to go at C. You're going to open to CA, just like that. And then you're going to draw a circle. And what you're trying to achieve is this second intersection between your given line and your circle. Then, here's the magic part. You're going to take your straight edge, and I'm going to hold my pencil at C. I'm going to move my ruler till it makes contact. Then I'm going to pivot around, and I'm going to move my hand so you can see in a minute. So what I've done here is I've lined up B here, C right here, and then I'm going to draw this line in here till it meets the circle on the opposite side, and then we'll call that point D, and then I'm going to use my straight edge, and I'm going to connect D to A. And there we go. I've established a perpendicular to the end point of a given line. Now, with the 3 cases of perpendicular lines that you just learned here, if you're going to go to, well, let's say, I think in terms of a building, but you could be doing anything. Let's say that you're an artist and you want to lay out a template on a canvas. Or let's say you're a quilter and you want to lay out a pattern for a quilt. Or let's say that you're a furniture builder and you want to lay out a pattern that you're going to have on a conference table, for example. You have to know these techniques because it's all the same, whether you're building a house or whether you're building a quilt, or let's say, in some of my projects we've used tile patterns, we've used mosaic tiles. Well, you lay out the pattern, and essentially we create a nice flat floor with nice clean plywood, and we draw the pattern on the floor. Then we bring in our tiles, our mosaic tiles, and we lay them according to the template or the pattern that's already on the floor. And it would be the same, like I had a student one time that was, his hobby was stained glass windows. So what he would do is he would create a template out of like poster board or something, and then he would use that to pre-cut all his pieces of glass before he leaded them together. But it all began with knowing how to lay out, starting with the perpendicular lines. So here you've got three cases. Now, usually the one that people need to practice a little bit, the most complicated one is the one I just showed you. So why don't you do that one more time, start from beginning, see if you can do it from start to finish, draw your horizontal line, establish an end point, and then establish a center point, then draw your arc, just like we did here. See if you can duplicate this. And again, really the learning of this, the mastery of this comes in repetition. Doing these drawings over and over again until they're not just in the paper, but they're in your mind. That might work. Cool. All right. Pardon me? Zenith is never the same place. No, it constantly changes. It constantly is moving. Because just as your position on the earth is constantly moving, the zenith is, it's fixed relative to the observer, but it's constantly moving relative to the dome of the stars. You got that right. Good. So that's what you've been there thinking about for the last 5 minutes. Okay. Yeah, the zenith is constantly moving. So when you've got that plumb bob, if you think of it as an arrow pointing upwards, you know, the earth is rotating, so that's constantly moving with respect to the heavens. It's like hanging upside down. Well, sure. We can go with that. Well, okay, if it makes sense to you, that's the important thing. So, as a rule, though, I don't require people in my retreats and stuff to hang upside down. But that may not be a bad idea to try it. Okay. How you doing back there, Jim? You getting it? All right. Yes. What about the 3, 4, 5? Well, okay, so the 3, 4, 5 you certainly can use. However, think of this. In order to use the 3, 4, 5 triangle, you've got to have two lines, right? Now what I do is, how to explain this? Well, okay, so I establish a line, and then I get my perpendicular to that line, and I eyeball it as close as I think I can get it. Like what I've done is, like you create, on the building site, we call them batter boards. So we have, like if you can picture, if we've got 2 posts in the ground, and then we have a horizontal like this, right? If you can see this. There we go. So then picture that this is a horizontal board, and I'll take a line, like go back to the drawing we just did. I'll take a line and I'll stretch it, and I'll put it here, and then we'll measure, let's say, 3 and 4 along the 2 lines we want perpendicular, right? Or I'll do 6 and 8, or whatever, any multiple of that. Then you carefully, like you'd mark, for example, if I do this, watch this. If I go here, you can see this, I will go 3 this way, if you can see that. Then I'll go 4 this way. Then my diagonal should be very close to 5. And if I go here to 0, I don't know if you can see that, but 0 here, and that's 5 inches. So what I would then do is I would take another measuring tape and I would start at one of the points, and that line would be adjusted until it was exactly 5. And at that point in my horizontal board, I take a saw and I make a kerf, which is just a little notch, right? Then I stretch my line into that notch, and on the opposite side of my board, I have a little nail or something that I can tie it off on. And then once, that's for starters. Now for really fine tuning, let's say we've got a big rectangular floor. Like if this room was rectangular, imagine any rectangular room. Well, if you measure the diagonals of a rectangle, they should be exactly equal. So if we measure the diagonals and one's a little longer than the other, we know we have to make some adjustments. So then when we're building, we constantly fine tune as we go. Does that make sense? Yeah. It's really quite fun. And you know, a lot of the skills that I've learned through the years of building with my, you know, I work with my younger brother we have a company, and our lead man, we're all getting up in years. Between the three of us, we have over 150 years of experience. And a lot of these techniques that we're learning are being lost, which is too bad. So one of my goals and dreams with starting a school is to have an apprenticeship program where these principles can be taught to a new generation and applied, because there are consequences to using these methods and these systems. And the ultimate goal of using sacred geometry in any kind of building or composition or design was to achieve harmony. So, how's this working? Did this work for you guys? Oh, excellent. Okay. Are they seeing this? Who modern surveyors?
Like if you were looking through your survey thing, is this what they're seeing?
No, not necessarily, but okay, so typically we use a builder's transit because you know what this is, it's like a telescoping tube, and you're looking and you've got crosshairs. And you level it out so that you can pivot that tube 360 degrees, and you've got a bubble level in there. You level it up so you turn it 360 degrees, and your bubble stays between the two lines, right? Then you can pivot it around this way, and then you can also pivot it this way, right? So with that, you can do a lot of things with that, right? But yeah, we'll like I might do, I'll have a foresight and a back sight. So I might, like if I'm going to lay something out and I know my east-west axis and I want to have my building line up, exactly with the position of the summer solstice sunrise. Well, now I can use, in the old days, it was the result of observational over, many, many years. Now, of course, I can look at an azimuth table and I know whatever my latitude is, I know exactly where the sun's going to rise on the horizon, with adjustments for whether there's a hill or, because those azimuth tables are laid out according to a theoretical flat plane. But I can get that position, and I have my vernier scale that's on my transit, and I can rotate that, like let's say it's 25 degrees off of north. So I can rotate that according to my vernier scale, and I can look at the horizon, and then I'll have somebody with a pole standing out there, and I will tell them, I'll adjust them until they line up with my vertical axis within the crosshairs. So yeah, I mean, there's no reason to not use modern technology. Like now we use lasers a lot to line things up. They didn't have lasers back, the Greeks or the Egyptians or the builders of Stonehenge didn't have lasers, I presume. But, you know, you can accomplish the same thing, manual techniques, but hey, you know, this is 21st century. Isn't this the 21st century? Yeah, so this is the 21st century, so there's no reason to not employ modern tools and technology. That's my philosophy. But here's the thing, the stuff that we do on the paper, even though I might be using a transit and a modern builder's level or a laser or whatever, you still, if you're gonna lay this out onto a building site, if you're going to, you know, create a pattern that's gonna be on a compass that you're gonna paint, or, I mean, on a canvas you're gonna paint, or whatever the case may be, you need to know these techniques. Now, I do a lot of digital design, and it's really fun to do this kind of stuff digitally. I create three-dimensional models of the things that we're gonna build, but it starts with a two-dimensional pattern, then I go to the third dimension, and the software I use, you know, I can rotate around, I can put the sun in the sky, and I can move the sun to any time of day, any time of year, relative to the latitude of the structure that I'm designing, right? Which is a whole lot of fun. Now, there's a lot of shortcuts, really cool shortcuts you can use in a CAD program or you know, a Photoshop program or whatever the case may be. However, even though you can do that digitally, if you want to take that digital template and transpose it onto a real world material thing, whether it's a building site or a canvas or whatever, that's where you use these techniques, right? Is that making sense? Okay, so let's get a clean sheet of paper here. And we're going to look at some properties of a circle. So let's set our compass maybe to roughly about a 3-inch radius, just roughly, and draw you a nice clean circle, and then establish a point that would be roughly at 12 o'clock, high noon. And once you've got that, make sure, be very careful, don't change the setting of your compass. And regularly check the wing nuts to make sure that they're snug. Now, place the metal tip at that point. Let's see, let's just go ahead and call it A. Place it at point A, and then what you're going to do is you're going to strike off 2 little marks, one over at roughly 10 o'clock and one at 2 o'clock. Just like that. And we'll call those B and C. Now, once you have B and C, you're going to use those, again, this is the logic of geometric drawing, you'll be using those 2 points as centers. Be very careful, you do not change the setting on your compass. First use B, and then you're going to swing and make a little arc down that would be at roughly 8 o'clock, if this was a clock. And then one from C, that will be roughly 4 o'clock. So I'll call these D and E. And then you're going to use D and E, and here will be a measure of how accurate your drawing is. You're going to use either E or D first, doesn't matter, and you're going to mark off that would be like 6 a.m. on your clock. Then you're going to go over to D, and you're going to draw a second little arc, and hopefully they should cross very close. Because an interesting property of a circle is that the radius of any given circle will exactly step off around the circumference of the circle 6 times. And it'll be, you can prove that it's mathematically exact. Then once you've got that, let me see if I can use one of these colored pencils. No. Well, no. B and C need to be exactly the same as the radius of the circle you drew. No, if it was arbitrary, it would not, I don't know what you'd end up with, but. Yes, it would be profane, undoubtedly. Now, what I do at Sacred Geometry Retreat, what I do is we create these tote bags, and as part of the tuition, you get everything you need, which includes the calculator, which includes colored pencils. Look at these, awesome. Now, this is a pretty fancy set, but you know, if you're going to be a professional, you got to have a fancy set, right? But you can see here. But yeah, we usually include a set of colored pencils and colored pens, 2 different types of compasses, and several other cool things, so that you got everything that you need to participate. And of course, you're welcome to bring your own stuff too, but I found that without standardization, it gets kind of tricky sometimes, because you got one weekend and you're trying to get to a lot of material. And so one of the things I learned early on was get some good helpers to circulate around, because I would say, if you get stuck, raise your hand, and then 3 hands go up, so I'm out there helping somebody while everybody's waiting for the next step. So like the last retreat I did, I actually had 5 helpers circulating around. We had 50 people, and we had 5, so that was 1 helper per every 10 person, and that way we're able to keep the pace up. You get stuck, raise your hand, your helper will hurry over and help you figure out what you're doing wrong or what you need to do next. So after I did this, I went ahead and I drew a hexagon in there. I should have told Beckett to put out that if you wanted to bring your own colored pens and pencils, you should have, but it's fine. Hopefully you'll retain enough of this when you go home, and you will have the video available so you can re-watch it. And then what I'm planning is sometime late fall or early next year to do what I'm calling a second level, an intermediate level sacred geometry, because you got to get the basics down first, and then once you've mastered the basics, then you can move into the really cool stuff, and that's where you can get into where the ancient builders and the ancient use the symbolism of geometry to encode information and all kinds of things. And then you can begin to decode that and learning how. And what happens is, once you've immersed yourself into the realm of geometry, you start looking around you, and especially if you start looking at, if you look at the pyramid, Great Pyramid of Khufu, for example, it's a repository of geometric sacred geometry. We may be able to get to that today. I don't know, we'll see. Typically, when I do a weekend workshop, the last one I did, so Friday night was a lecture with no drawing, and then Saturday and Sunday were all day drawing, learning the techniques, and then Monday was a field trip. We did one in eastern Tennessee up on the Cumberland Plateau, and about 20 minutes away was Sewanee, where the University of the South is, and there's the chapel there that was inspired by Chartres Cathedral in Amiens, and it's got symbolism and sacred geometry in it. So we did the field trip to see how the designers, the architects, encoded this stuff into that particular chapel. So it's embedded in things all around us, both human-made and natural. Okay, so have everybody drawn a hexagon? Absolutely. What's your name? Travis. Yeah, Travis just pointed out Native Americans. It's quite surprising the extent of geometric knowledge employed by Native Americans. One of the things we're going to learn today, shortly coming up, is to draw what's called a root 2 rectangle. It's one in a family of rectangles called dynamic rectangles. This was well known to Native Americans. And many of the mound structures, you know, when you look at them and you understand the geometry behind them, you'll look at them with fresh eyes, and you'll understand. You'll look at some of the mounds and you'll realize some of the truncated pyramids are not perfect squares, they're rectangles. And they're rectangles that are based upon what we're drawing right here and what we're going to be doing in the next hour or two. So now you've got this. There's a number of things you can do with this. Now, of course, we can create the famous Seal of Solomon simply by connecting alternate vertices. In geometry, we call the corners vertices. So I'm going to do that right here, and you'll be able to see that I'll just draw 1, 2, and 3 here. Whoops, sorry. Part of my problem is to see I'm not over. My paper is out here, so sometimes it's difficult to get things to line up perfectly. So I boo-booed here, but you get the idea. If you draw A to D and D to E back to A, you'll have an equilateral triangle. And then if you do the same thing, B to C, and we'll call this one down here F at 6 o'clock, like this, then you get the hexagram. The hexagon is the 6-sided polygon. The hexagram is the 6-pointed star. So an octagon is an 8-pointed polygon. An octagram is an 8-pointed star. And then this is where you can start to see where the sort of the fractal properties come in, because you'll see that inside that star you now have another hexagon. So I'm just going to draw that in like this. Pardon me? It'll be 6 lines. 2 triangles, 2 equilateral triangles, 3 lines composing each triangle. You know, and then you can have a little fun with it if you want. You can color it if you want, just Pardon me? Yeah, the Star of David. Yeah, and so right there, you see they were encoding a geometric meaning into the symbol of their religion. And what happens is this 6-fold. Have you ever heard of Kabbalah? Okay, so in Kabbalah, there's a system called Gematria, which is basically this idea that in the ancient Semitic languages, before the advent of the Hindu Arabic numeral system, the same set of symbols, whether the Greek letters or the Hebrew letters, were also the numbers, right? So what that meant, and typically your mainstream religious view, whether you're Christian or Jew or Muslim, doesn't recognize any significance to that fact. But there's a whole school. There's a Greek Kabbalah and a Jewish Kabbalah. Jewish Kabbalah, of course, is based upon the Hebrew alphabet, and the Greek Kabbalah is based upon the Greek alphabet. Well, for example, In the Hebrew, you have Aleph, Bet, Gimel, Dalet, He, Va, Zain, Het, Tet, Yud, etc. through the 22 letters. In the Greek, you've got Alpha, Beta, Gamma, Delta, Epsilon, etc. through the 24 letters. Well, each of those represents a number. Like Alpha, Beta, Gamma is 1, 2, 3. Delta is 4. Epsilon is 5, right? Then you get to Iota, which is a 10. In the Hebrew, you get to the Yud, which is a 10. And when you actually look at the way the Hebrew letters were drawn, they're drawn with a flat stylus so that I can't demonstrate. If I had one, typically in the retreats, I will demonstrate how the Hebrew letters were drawn. But basically, the idea is that the Yud was the seed of the whole alphabet. And if you look carefully at the alphabet, you'll see that all the other letters are elaborations or permutations of the basic Yud that essentially looks like this. I'll draw one here. So that's what your Yud looks like. And that has the value of 10 in the Hebrew alphabet. It corresponds to the iota in the Greek, which also has the value of 10. So it goes units, tens, and hundreds. So, okay, so the implication here is that words, names, phrases, etc., if you took the name like Yahweh, which is a Yud, He, Va, He, Yud, He, Va, He, it's 10, which is the Yud, He, which is a 5, Yud, Va, or Vau, which is a 6, and a final He, which is another 5. You add them together, you get the number 26. So the number 26 was then associated with Yahweh, right? That's just an example of how it works. So once you understand that, you can go in and you can go back, like I've done this, you do Kabbalistic research or research in Gematria. If you're interested in that, what you do is you get yourself like an interlinear Greek New Testament, but there was a lot of, it wasn't just the New Testament and the Old Testament. Old Testament, you know, was written in Hebrew, the New Testament was written in Greek. But there's a lot of other things as well, a lot of the Gnostic writings and so on also have this Gematria system, where you can take a name and then you can substitute the values, the numerical values of those letters, and you get another number. Okay, so why do that? Well, it would be meaningless and of no significance if all you got was a whole series of random numbers. But it's far from random. What you actually discover is that those numbers that recur reiteratively and over again are associated with geometric forms. And what that means, in my mind, is that there's multiple layers to the sacred writings. And the outer, the literary layer, the stories, the parables, the metaphors and stuff that you find described in the literary version, if you peel that back and you look at what's underneath, there's a whole realm of mathematics that almost nobody knows is there, except, you know, people who've studied into this kind of stuff. And, you know, there was a time back when I was first learning all this in the late 60s and early 70s when I thought, wow, we're going to discover that this is here and that there's this probably a whole scientific layer underlying the outer literary version of it, but it hasn't caught on. I mean, I think it's even less known now than it was 50 years ago. A lot of this has been forgotten, but I can show you, and this is what we get into in some of the intermediate and advanced classes. I'll show you that, you know, just like we do the hexagon here, right? So each of these angles, between each of the edges, you have angular measurements, right? So you've got 360 divided by 6, which is 60. And then each of those degrees has 60 minutes. So 60 times 60 is 3,600. Then each of those minutes of arc have a second of arc, which is 60 times 3,600, which is 21,600. Okay, so those numbers, it turns out, we can find reiteratively embedded in the Kabbalistic interpretation of sacred writings. So what that then does is it opens up the sacred writings to a whole nother profound level of meaning that I think is still waiting to be discovered. And basically what it does, I think, is showing us is the key numbers of harmonic frequencies by which we can control matter and energy, particularly in the realm of plasma physics. And this is why one of the numbers that recurs over and over and over again is the number, say, for example, 432. And 432 is the basis of the Sumerian king lists, right? If you add all the 10 kings of Sumeria together, you get 432,000. Then you shift over to the Vedic traditions of the great cosmic cycles, the yugas and the kalpas. And what do you discover? Well, the basis of the whole yuga cycle system in the Vedas is 432,000. And it has multiple other places where we find it as well. So how many seconds are there in a day? Well, so this is where we would do, this is an example of where the calculator comes in class. So if I have, let's see if I can get, so that's 0. So think about this. How many seconds in a day? There's 24 hours. So I put 24 into the calculator, right? Then there's 60 minutes per hour. So I go times 60. And I get this number, 1,440. Well, that's one of the key important numbers too. We find that it's one of the Mayan time cycles, 1,440 days. We also find reference to this in the 144,000 redeemed of the earth that's described in the book of Revelation. We also find in the book of Revelation the description of the holy city, which is 12,000 furlongs on a side. It's described as a cube. The length, the height, and the breadth of it are 12,000 furlongs, okay? Well, then you take the furlongs, it's described as also having a great circular wall around it, which is 144 cubits. It says, according to the measure of a man, that is of the angel, which is interesting because ultimately these numbers do also relate back to the ultimate embodiment of sacred geometry amongst the organic realm, which is humans. So anyways, it's very interesting. I said furlongs, right? Does anybody know where furlongs, which is one of the ancient units of measurement from the imperial system, which we inherited from ancient Greek? Ultimately, I think the builders of Stonehenge were using the imperial system of feet, inches, yards, furlongs that we're still using. Where are furlongs still used? Horse racing. A furlong is 660 feet. Now let me show you something. You asked, this man in the cap there, you asked if it was just a coincidence. So what I'm going to do is I'm going to show you here, I'm going to put in 660 feet. Right? The number of feet in a furlong. Now there's 12 inches to a foot, so I'm going to go times 12 equals, did we just see that number somewhere? Yeah, it's the Earth number again. How did that end up there? Coincidence? Well, yeah, we can say, okay, well, there's 2 examples of that number showing up, so yeah, it's coincidence. At what point, though, does it stop being coincidence and being a meaningful pattern? Say again? Of course, but now, is the division of a circle into 360 degrees arbitrary? Of course not. For one thing, 360, you've got to come up with a number where you can have a lot of subdivisions of it. For example, if you've got a pie and you want to be able to have the maximum number of slices with nothing left over, 360 degrees is a great one to use because you have a lot of numbers in there that are divisible into 360. So you can get a huge number of slices. Think about it. 2, 3, 4, 5, 6, not 7, 8, 9, 10, not 11, 12, etc. will all divide evenly into 360. Now, according to tradition, and most of the, and I'll show you the quotes here in a few minutes when we shift from drawing to I'm going to show you a slideshow. Most of the, if you read the history of geometry, it's usually attributed to the Babylonians, although I think it long preceded the Babylonians, but historically It shows up in Babylonian architecture and Babylonian writings and so on. And the usual interpretation of it is that the Babylonians believed that the length of the year was once 360 days, and then there was some great cataclysm or something, and that nice synchrony got upset, and it became 365.24 roughly in a year, okay? Days in a year. But that was the idea, that the Babylonians believed that the year, along with a lot of other cultures, believed that the year was once 360 days, right? So now, if there's 24 hours in a day, 24 hours times 60 gives us 86,400. Let me see, we can put that up there. So that's the number of seconds in a day, 86,400. Well, what happens on the equinox? Well, equinox translates as equal night, meaning the night is equal to the day in length, right? Now, when most people talk about equinox, they're thinking, oh, today is equinox, right? March 21st, March 22nd. Well, it's not a day. It's a mere moment. And it has actually no definition. How many of you guys have ever studied calculus? You know what a limit is in calculus. It's something you approach closer and closer and closer, but you never actually get there, do you? Right? It's like Zeno's paradox. You never get there. Well, equinox is like that because we're talking about a system that's constantly moving, in motion. The Earth and the Sun are moving constantly relative to one another. The Earth doesn't stop at that moment of equinox. But there is a moment that we can define. If we define it as a piece of a second, part of a second, we could say, okay, here's this theoretical limit, this moment here, where day and night are of equal length, right? So then we divide our 86,400 seconds, as we see there, by 2. And this is what we get. Okay. 43,200 seconds of day, 43,200 seconds of light, 43,200 seconds of dark. What? Say one more time. It's not the golden ratio. No, it's not the golden ratio. But the golden ratio does fit in here. But, okay, so this is what I'm trying to get at. Now, these numbers will show up in the forms and the measurements of the geometric forms that we learn to work with in sacred geometry. And it turns out that for those of you that have heard about the thunderstorm generator, it's a series of concentric spheres and concentric cylinders that sets up these coherent plasmoids out of random chaotic plasma motion. And the ratios of the diameters of the cylinders and the spheres is 4 to 3 to 2. And if you change those ratios, it doesn't really work effectively. But if you have those ratios, 4 to 3 to 2, so there's, again, this is pointing the direction that what we're ultimately looking at here is frequencies, vibrations. Think about in our octave system that we use now, 440 is your A and your octave is 880, but in the ancient system was 432, was the basis of the octave system of tuning. So then your octave went from 432 to 864. What's that? I'm not quite hearing. Is there we need to have a microphone we can pass around for questions. Say again. Oh, why did they change to 440? I'm not quite sure. I mean, I know there are some people out there who have made deeper studies of this than I have and have reasons and explanations why they think they did that. I don't know. Other than, I don't know. It changes the vibratory environment. Yeah, okay, that makes sense to me. So yeah, I mean, there's a movement to try to get back to a 432 tuning system. Yeah, if you want to read more about it, you know, there's several sites online that are doing some interesting work with that. And that's, I'm not a trained musician, I'm a percussionist, but I'm not a trained musician, so I know beats and rhythms and stuff. But anyways, there are sites online where you can read some interesting stuff about the 432 tuning system. Yeah. Say again. Ah, there we go.
Yeah, my question is do these geometric patterns, these numerical patterns, relate to what we see in cymatics when we look at frequencies?
Yes.
So there is a sound to sight correlation.
Yes, you'll see a lot of correlations between the patterns we're doing here and the patterns that show up in cymatic phenomena. Yes. Hand her the microphone.
You give an example for cymatics. The nodes that you see in cymatics, how do they relate to the points that you see in sacred geometry?
Well, typically, you know, you have, mostly in cymatics, I think you've got radial, you know, you have a point, a center, and I think most of the phenomena you see is ultimately referable to a central point, if I recall, from the patterns that I recall seeing. So, I mean, we get into drawing a lot of different polygons that can be divided into, you know, six sides, like this is a hexagon, 5 sides, 7 sides, 8 sides, 9 sides. Within those, you can create all kinds of compositions using that. And what we would need, and I have some, but if you look at some of the patterns of cymatics, you will begin to see these geometries in there. Okay, so now, are you running out of paper? Beckett, what's our paper situation?
We've got more.
We got more? All right. I'm good for a moment. I think some people out there need more paper. You guys need to take a 5-minute break, get coffee or go to the bathroom or anything? All right, looks like we've got some paper coming here. Okay.
If everything is in constant flux,
Okay.
are we measuring vibration and its association with another vibration?
Yes, I think we could say that. I mentioned that vibrations. I mean, that's what this is. Frequencies, cycles per second. See, 432 cycles per second is A in that tuning system.
Very difficult to hear back and forth, but my
You're
question,
having difficulty hearing me?
it's more hard for you to hear us, I think.
Yeah, that's right.
You have a microphone, we don't.
Right.
My question is, why do the size of the sun, the moon, and the earth fit this system only if you use miles?
Only if you use what?
Miles.
Well, I mean, okay, so the ratios are constant no matter what the dimensions are. You know, in other words, the sun is 400 times, the diameter of the sun is 400 times the diameter of the moon, regardless of what you measure it in. However, when you use the ancient system of metrology, that's when you see the sacred numbers show up. So the sun, measured in miles, is 864,000 miles. And its radius is 432,000 miles. Now, where does the mile come from? Well, if you remember what Protagoras said, man is the measure of all things. The idea is that we're the ultimate embodiment of sacred geometry. So, the ancient system of measurement was based upon two things. It was based upon the human dimension, the inch, the cubit, right? Here's your cubit. The foot, obviously, your foot. The stride, you know, as you walk, your pace or your stride. The span, which was this, which also gave us the fathom. All of these are measurements based upon standardization of human dimensions, right? A mile was 1,000 paces, right? In Latin and Greek, mil is 1,000, right? So if you go out and you take 1,000 paces, and if those paces are standardized, and of course it's different for, obviously, the larger the person, the greater the stride. There's cultural differences because some ethnic groups are smaller than others, right? The point is, though, if you take a lot of data points and you average them, you come up with certain numbers. Now, how many feet are there in a mile? We got it here. Do you know? How many feet in a mile? 5,280 feet. Well, a mile, again, comes from the root mil, which means 1,000. So 1,000 what? Well, 1,000 paces. Well, so we can deduce from there that the mile is 1,000 paces. Our modern, I call it the imperial mile because it's descended from the ancient British system that we find. I'm almost certain that the builders of Stonehenge were using the same system that we're using now, and I give you some examples in a second to support that conclusion. But if you take 1,000 paces and you get 5,280 feet, well, then it means that the average pace is 5.28 feet, right? 5.28 feet. Now, the Roman mile is shorter than the British imperial mile, and that had to do with the shorter stature of the Romans compared to the ancient Brits. So what you end up with is different miles for different cultural groups, okay? But our system has been standardized to a pace of 5.28 feet. So 1,000 of those gives us the mile, 5,280. So what is happening here is the mile is a unit of measurement that shows these harmonic numbers that link the human proportion to the cosmic proportion. If you show it in meters, the ratios are still the same, but the sacred numbers, you don't see them. You miss them, right? If you convert the moon's diameter is very close to 2,160 miles, which means it's got 1,080 miles in the radius, which is about 1,738 kilometers, right? But it's 1,738 point something kilometers, right? And it's about 1,080 miles. Well, 1,080, here's your number 9 again, right? Same number, it's 10 times the number, which is the angle of the pentagon. And the pentagon, if we're trying to show the interconnectedness of this system, the pentagon has 108 degrees between each side, right? And all of the polygons will display these numbers, right? So we're going to see examples of that as we proceed. But there's a lot of interesting things here. Well, like, for example, if we take the dimensions of the holy city in the book of Revelation. The city lieth foursquare, the length, the height, and the breadth of it are equal, which would suggest it's describing a cubical structure. But the length of the side is 12,000 furlongs. So we just found out that a furlong was 7,920 inches, right? Well, 12,000 furlongs will be 7,000. Well, let's put this in. I'm going to do 12,000 furlongs. So there's the 12,000 right there. Furlongs times 660. So the number of feet in the side of the holy city is going to be 12 times, a furlong is 660. So there's 12,000 of those, so times 660, and look at the number we get. Lob off 3 zeros, and what do you got? We're back to our Earth number again. Well, as Malcolm Bendel points out, the number of zeros really doesn't matter because we're ultimately looking at a fractal harmonic system. So it doesn't matter whether we're talking about 864,000 vibrations per second or 86,400 or 864 or 432. It's in the ratios that are important, right? Okay, so now this number, 7,920,000, that's the number of feet. So we're getting this geometric metaphor in the book of Revelations in the description of the holy city. 7,920,000 feet on a side. Well, how many of you got a calculator in your phone? If you want to, get your phone out, and good man, get your phone out, open your calculator, put in 7,920,000 feet. Now divide that by 5,280, the number of feet in our mile. So divide by 5,280, and you get a nice round number, 1,500 miles. Okay, 1,500 miles is the side of the holy city. Now, do this. 1,500, what is our Earth number in miles? 7,920. So what we're going to look at now is the ratio between the Earth, the size of the Earth, and the holy city. So put in 7,920 and divide by 1,500 and tell me what you get. You get 5.28. The ratio of the pace to the foot in the ancient sacred imperial system of ancient Britain. Now, is that a coincidence? You think it's a coincidence? Or are we getting to the point where these numbers occurring are rapidly moving beyond any hope of dismissing it through coincidence? So in other words, think about this. We're standing on the earth. Our feet connect us to the earth, right? Our foot is standardized now at 12 inches, which is 12 of these, right? That's where the inch comes from. It's the width of your thumb. So from now on, whenever you give somebody the thumbs up, I want you to be contemplating that. You know, here's the basic unit of the ancient imperial system. So you're not just going, hey, you're going, hey, you're telling this person, hey, basic unit of the imperial sacred geometry system of measurement. So, anyways, so now you've got the foot and you've got the pace. So the pace is you're moving over the surface of the earth. The foot connects you to the earth. And that ratio, as it turns out, is exactly the same ratio as the earth to the holy city. Well, again, this is like peeking into the fractalization of time and space, right? So if it's not coincidence, then what's the explanation? Well, the explanation is that there is reiterative, what do we want to call it? We call it self-similarity. That's one term we can call it, self-similarity. Fractalization, scale invariance is another term that we could use to describe the system, because what it's trying to do is show us the common measurements between the human domain and the cosmic domain. So let's learn how to divide an angle into two, because that's always an important thing as well, being able to bisect an angle. So what I'm going to do here is I'm going to just draw an angle kind of at random. Then, at the vertex of the angle, I'm going to strike off 2 marks equidistant along both sides of the angle. And I'll call them A and B, and this will be C. So now we're going to use A and B as centers. And watch what I do here, so you can see 1, 2. And I'm drawing them nice and big so you can see them. And then, where those arcs cross, like this, I've now bisected that angle. I've taken that angle, I've divided it into 2. So when you are doing these geometric drawings, typically what I teach people is when you're laying this thing out, let's say you decide, I want to do this really cool pattern based upon 8-fold geometry. So I'm going to lay out a pattern on my paper, and then what you're going to do is typically when you're setting up your construction, your geometric construction, you draw very light lines, right? We call them construction lines or temporary lines. And then once you've got the pattern and you're happy with it, you then can come in and use darker lines or permanent, like ink instead of pencil. So we call your permanent lines and your temporary lines. Temporary lines are like if you're building a house or a building and you use scaffolding, and then the scaffolding is just temporary. You're using it to get up and build your cornices and whatever. When it's done, you take the scaffolding down. It's just temporary to get to your basic structure. So think of that in geometric drawing. You use temporary lines and permanent lines. So today, we're not going to get past learning too much the basics, but as soon as you move beyond this, typically like in a weekend workshop, we're going to have 3 hours today, but in a weekend workshop, you will typically have 10 or 12 hours of drawing spread over a couple of days. So by the time we work through the basics, we can start getting into some of the really cool stuff. And I'll turn people loose and I'll say, okay, we're going to do imagine that you're doing a stained glass window, and it's going to be an octagonal shaped window, and you're going to do some 8-fold geometry within that design. And so now you know the basics, you know how to set up an octagon, you know how to subdivide it harmonically, so go, get creative. Draw the thing, get out your colored pens and color pencils and go crazy and have fun with it. Imagine that you're in kindergarten again or whatever. And but you got to have the basics. So, that's the thing I explained to Beckett. They're only going to be able to go so far in this because this is. At first I was thinking, okay, what I'll do is I'll just sit up here and I'll draw some really cool patterns and you can watch. And then I'll show you the slideshow. Here's this pattern showing up in a stained glass window in Chartres Cathedral or Amiens, or here's this same pattern you find laying out the octagons at Newark Earthworks up in Ohio, or wherever it might show up, right? But I thought, Beckett said, well, let's have it participatory. And I thought, well, I mean, people need to have drawing supplies and all of that. He said, well, I'll take care of it. And I said, well, let's do that then. So we're kind of doing this, and I'm hoping that at least some of you, I'm preparing an online course it's going to go through all of the basics. And it's going to be the same thing that's already online, because I've done a couple of workshops now, introductory, and we've recorded the whole thing. And those are available if you go to How To. And I forget what the cost of downloading, but it's pretty darn reasonable, actually. So in order to do the intermediate, in order to be able to go into the higher levels, I want to have the students be fairly, adept at drawing the basics. Because otherwise, we get bogged down. There's a lot to dive into here. There's a lot to unpack with this system. And so to get into the immediate level, intermediate or advanced levels, I want students to be, very adept at the basics. So if I get in there and I say, okay, we're going to need to, for this exercise, we're going to need to set out 2 parallel lines. You can do it. Or we're going to need to set out a pair of perpendicular lines perpendicular to the endpoints. You can do it. And you're not sitting there trying to remember what to do. So the idea is, if either the intermediate levels are going to be open to anybody who's done the in-house workshop, or who's gone through the basic material online, downloaded digitally, and gone through the exercises at home. Then we'll get into the intermediate stuff. And what I'm ultimately hoping, though, is growing out of this is revitalizing the whole system and putting it to use again. Because there was a reason why ancient peoples all over the world incorporated some variation of this system, was because it led to a palpable result of harmony that can actually be, I think, proven now with the physics we've got, and with the, with what she was asking about, the vibrations, and whether if two vibrations, two vibratory frequencies come together and constructively interfere or destructively interfere. Well, I think that's what we're ultimately dealing with here. If we build structures that are resonantly tuned to the planet and to the cosmos and even the microcosmos, we create harmony amongst those realms. And I think that was the whole point of it, ultimately, to literally to affect the vibratory frequency of the planet, or at least regions, local or regional places, and that would actually increase the amount of harmony amongst people. It's something I think we desperately need in our world today, because we really are standing at a crossroads right now, which direction we go from here. And we can go towards perpetual destruction and strife and conflict, or we can create a world of harmony. And I'm afraid it's going to come down to us, people like us who are in this room, and what we do over the next few years, which is going to determine the trajectory. I'm sorry, I can't hear. You're getting a mic over there.
Thanks. Yeah, do you consider that what happened in the 1930s to the mid-40s an aberration in history? Because they certainly used the manipulation of sound to manipulate the people and to feed the hatred that was stemmed from their loss in World War I. And the rise of an individual like Hitler and his minions, and also their interest in the occult. Their interest in the occult was very, very spooky, very strange in the things they tried to do.
Well, it depends on how you look. Occult simply means hidden.
Oh yes,
so
not seen.
There was occult knowledge that had to be hidden because some occult knowledge liberates the individual. And what we're talking about learning right here was considered occult, right? Because a lot of those in power who want to control people, there are certain things that you're not supposed to know. And what was one of the primary techniques for cultivating critical thinking skills? Well, geometry, right? So if you have something that's promoting critical thinking skills, well, those that want to hold us, enslave us to contrived narratives don't want us to be able to think critically. Otherwise, we see through their deceptions. So, for example, throughout many centuries, Freemasonry was outlawed. When Stalin took over, the Soviet Union, he outlawed Freemasonry. Hitler outlawed Freemasonry. Pol Pot outlawed Freemasonry. That's a very typical thing, to outlaw Freemasonry. Why? Because the basis of Freemasonry was sacred geometry and the teaching of critical thinking skills and the development of the mind and so forth. So this is not something that dictators and authoritarians and despots want, is people to develop their minds and their independent thinking skills. And you've got a comment you want to make. Yes, let's get back to that. But this is all part of the context in which we need to understand sacred geometry. It's been handed down through the centuries. It's been suppressed sometimes. Other times it's been honored and respected and utilized, and it's led to positive outcomes. So it's not just about drawing figures on paper. It's about understanding the larger context of why so many cultures in the past used it and chose to use it to create their sacred spaces, their temples, even the structure of their sacred writings. Are you cool with that? Okay, good. Let's do an octagon then. And I'm running out of paper. Oh, thank you. All right. So for this, and what I want you to do, and we're going to do this in pencil, and it's going to be light, because the first thing we want to do is a square. We're going to draw a square, right? So then, to draw this square, there's a number of ways that you can draw an octagon, okay? We're going to start by drawing a square, because the square gives us half of an octagon, basically. So what you're going to do is you're going to use the technique that we learned. You're going to set out a line, and let me see here if I can use my pencil, and hopefully you can see this. And then you're going to do the perpendicular to the end point of a given line, like this, like we just learned. See that? Or is it too light? All right, so I've got, if you can see, if you want to take a look at the screens up here, you'll see what we're doing. So here's a given line with an endpoint defined, and then I've established sort of an arbitrary dot, and then I'm using that as a radius. So the 2 points define the radius of a circle. The intersection of the circle with the line generates a third point, just like this. So this is what you're going for, right here. And then, if you recall, good. Over here, the circle intersects our given line. And you can see the next step would look like this. And then like this. So I'm going to leave this up here for a moment because this is what you're going for. Now, of course, when we've got a full weekend retreat, you would learn why we know this is a 90-degree angle. Now you're just going to have to take it on faith, I'm afraid, that this is a 90-degree angle. But it's very provable within the propositions of geometry. Anybody here ever had a course in geometry in 8th grade and you forgot 99% of it? And what? Was it? Okay, yeah, mine too.
Did you connect music to this first?
No, later. I mainly came at this through the portal of architecture. I was interested in, which goes back to the early 70s, 73, 74, 75. I was exploring the geometry of sacred architecture. And that's where I discovered that they were using pretty much variants of the same system all over the world and over a period of thousands of years. So this is your right angle here. Now, let's see what I do next. So what I'm doing is I'm extending my vertical line, and then I'm going to get rid of what I don't need. Let's see. Okay, so what I'm showing you here is something you don't need to worry too much about now, but once you get more experience with drawings, for example, to get this right angle right here, you don't need to draw all this, do you? Because really all you need is the key points that I'm showing right there. Is that making sense? I'll do it again so you can see. Here's what you've drawn, and if you're going to understand why this works and why you know it's 90 degrees, this diagram is how you prove it. But you don't need this. If your point is just to set out two perpendicular lines, you're going to minimize, you're going to try to keep your marks on the paper to a minimum. And that's what I'm showing you right here. And really then all you need to get this. Once you have that, and that's what you're going for, see how we get rid of everything except the two perpendicular lines? And you'll notice I've got a little hash mark down here. And as it says, the existence of two perpendicular lines can be used to generate a square. Okay, so watch this and you'll see. Simply transfer whatever side length is desired. So I've just established a side length here on the bottom. Simply transfer whatever side length is desired for the square by marking off equal increments from the first point. So here's what I've done. Look at this. You see I've got a mark here and I've got a mark up here. And that's the same distance on the vertical line and on the horizontal line. Then I use those 2 points. Remember, here's the logic of geometry. I create points from which I can generate additional points and lines. So now I use those to establish that fourth corner. So throughout this, once I've established this length on my baseline, I don't change my compass. I transfer it to vertical line, and then I use those 2 points to get that fourth corner. Is that making sense how I did that? So that's what I want you to do, and then create a square out of it. Yeah, it doesn't matter which side you do it. You can do it either side. In other words, you could flip this diagram. That's up to you. Just exercise your godlike powers and go for it. So what you're going for is this. You want to make a nice, beautiful square on your paper. A square is a rectangle where all angles and all sides are the same. For
My grandpa did surveying with GW.
your grandpa was what?
Did surveying with GW.
Oh. Oh, he did. Okay. Then, once you've got your square, draw in the diagonals. What? Oh. What? No, I was just looking back there to see if Micah was getting stuck or not. It looked like, does Micah have his compass and paper? I'm concerned about you, Micah. Now, if your square, what's the simplest number? What's the loneliest number? Okay, 1. So oftentimes when we want to determine the ratios of different sides of anything, whether it's a square, or a hexagon, a pentagon, or whatever, we will use a base unit of 1. Like, for example, for a square, if we want to know what the length of the diagonal is, we'll just establish the side length of the square is 1, and then we'll calculate the length of the diagonal. So if you have a square of 1, the diagonal is going to be, you determine just by using the famous Pythagorean theorem, which tells you that the squares drawn on two sides of a right triangle are equal in area to the square drawn on the hypotenuse of a right triangle. And you can see here in this, once you've got a square, watch what I'm doing here. There's your calculation right there. Does that make sense what you're looking at? If you know basic, and really I do highly try to emphasize to people that some of the basic mathematics, it's good to know in life. Not only for the reason that learning mathematics and geometry helps to cultivate critical thinking skills, it's also useful. And I found for my purposes that, you could look at it and go, well, what would I use this for, right? Well, that's one attitude. My attitude was, I've learned this. Now, what are the things I can do with this? And then I discovered, hey, there's all kinds of cool, fun things I can do with this, now knowing this. And of course, as a builder, you need to know some basic mathematics and geometry, even trigonometry. But ultimately, everything comes from geometry. Trigonometry is an outgrowth. And you can see right here, what we're seeing right here is the evolution of geometry into algebra, because we're simply saying, when we say a squared plus b squared equals c squared, we're just applying letters to the three sides of this right triangle, right? So we're using symbols. And then once you learn how to manipulate those symbols mathematically, it's quite a powerful thing for solving problems. And that's why I always, carry a calculator with me on the job, because I'm always calculating distances, areas, all of that kind of angles. And then trigonometry is an outgrowth of geometry. Analytic geometry is where you begin to combine algebra with geometry. And then, of course, from there, that provides the foundation for getting into the calculus. What's the difference between all of the pre-calculus mathematics and calculus? Well, pre-calculus, you're dealing with systems that are non-moving, which are fixed in time and space, whereas in calculus, you're dealing with phenomena that's changing, which is moving, and so on. But as far as, if you're building a building or a house, or using it to build, let's say you're designing a piece of furniture, like my conference table in my studio is an octagon with inlaid wood in a pattern of geometry. Well, obviously on that level it's all stationary, it's all fixed phenomena. So you don't need calculus for that. But if you're going to get into anything that's moving or changing, then you start with that basis of the limit. And we're not going to get into that today, but all of mathematics ultimately traces back to geometry. And pretty much all of geometry traces back to what you're seeing right here, the transition into algebra, which is this simple formula right here, bequeathed to us by the great Pythagoras. And he probably didn't invent it, he probably inherited it. But notice what the numbers you get there. The diagonal of a square with side length of 1 is the square root of 2. How do we know that? Well, just look at the equation at the top. A squared plus b squared equals c squared. So a could be this side, b could be this side. And if you draw squares on that, you take the area and add those together, it'll be the same as the area on the hypotenuse. And then you can then see that what's 1 squared? 1 times 1 is 1, plus 1 squared again equals c squared. So c squared equals 1 plus 1. C is equal to 1 plus 1, which is 2. And then the side, which means that the side length of the diagonal is going to be the square root of 2. And this is the key now to the first rectangle in the system of dynamic symmetry. And this was used frequently in architecture, in sacred architecture. The whole complex of Angkor Wat, for example, in Cambodia, is all based upon the root 2 ratio and the rectangle that you generate from the root 2 ratio. So once you have a square with its diagonals, let's see here if I can. Okay, so there we have, by the Pythagorean theorem, it is easy to prove that a square with a side length of 1 unit will have a diagonal length of approximately 1.414 of the same unit, or exactly the square root of 2 times the square side length. So the root 2 rectangle comes when you use that diagonal of the square to generate the longer side of the rectangle, just like I did here. So this is the thing I want you to do next. Once you've got your square, you simply use your compass, like set your center at A, open to radius AC, and swing this arc down, and then extend your baseline out until it meets the arc at point D. And this is the first step in creating the dynamic root 2 rectangle. You remember how do you create the square? I'll go back to my paper here, and if we can switch back to the paper. Excellent. So what I'm doing here, I'm going to do the drawing so you can see. I've got this here, so I'm just going to use it already. So there, if you can see, I've taken that length. I'm transferring it here because this and this need to be the same length. Then I use those, watch this now, like that and like this. And that gives me that corner of the square. And then I can darken that in like this, and I've got a square. Then, the next thing I'm going to do is I'm going to take the diagonal of that square, and I'm going to extend this baseline like this, and I'm going to then set my compass radius to the diagonal. Hopefully you can see it right here. Then I transfer that to there. Then I'm going to do the same thing on the top. I'm going to draw that arc, and this should be the same as your diagonal. And then I'm going to extend this out to meet here. Then I'm going to connect this. And there is my root 2 rectangle. Okay, can we go back to the laptop? Good. Okay, so if you watch up here, you'll see what I'm doing. Taking that diagonal, and then I'm using it to generate this rectangle here. So the side length, the long side of this rectangle, is going to be to the short side, the same as the diagonal of any square is to its side. Hopefully that's making sense. Now, if you were going to create something that was going to be based upon a root 2 rectangle, let's say you're going to design a pattern for some reason, could be anything really. Let's say you're going to do a canvas. In fact, let's see, I should be able to switch over to another show here. And let's see if I've got some examples here. Yes. So here's a painting that's laid out according to a root 2 rectangle. So the frame is in yellow. And which is interesting, number of things symbolical that we won't get into too much today. But notice the vertical axis pretty much defines the point where the hand is holding this sphere. This is what this is representing is God using a compass to bring order out of the primordial chaos. This was a frontispiece to a medieval Bible. And the composition is based upon using a root 2 rectangle, like the axis here, the diagonal axis here defines the angle of the leg. You can see the vertical axis defines the point where the hand holds the sphere. Also notice that the foot is outside the rectangle. There's a reason for that. But it's all symbolical. Angkor Wat, Cambodia. So here is the ground plan of Cambodia, and here's a square juxtaposed upon the ground plan, and then there's the diagonal, and from that diagonal, we get the whole frame of the complex, all based on this root 2 geometry that you're learning to draw right here. And then on top of that, as this scholar says, numerically, Angkor Wat contains calendrical, historical, and mythological data coded into its measurements. Astronomically, it has built-in positions for lunar and solar observations. So not only is it oriented towards the movements of the heavens, it has this certain unique geometry built into its ground plan. But yeah, then you can subdivide this in a very interesting way to get replicas of itself. The root 2 rectangle, when I say dynamic rectangle as opposed to a static rectangle, the difference is that inherent within any dynamic rectangle is the ability to produce replicas of itself through simple geometric steps that you can take. Yeah. Okay, microphone's coming to you.
Is the portion of the temple to the left equivalent? In other words, does the square stop where the structure ends from,
This right here.
no, the far side, the other side.
This here.
From there to the end of the white structure.
Here.
Is that square?
Not quite, no. But if you include the steps coming up here, what happens is you get a square right here. When you look at actual examples, sometimes you'll find little variance because of the nature of the site, the nature of the available building materials, and so on. But as a rule, what you'll see is just like I showed you here, you can see that there's the square, and you can actually look, you can take it from the other end as well. And the portion that you get left over will be this side here. But if we go back to, let's see, this, and there are much more complicated examples, and I'm going to show you next how you find that dynamic nature of the rectangle. That's what I'm going to show you next. So what I need you to do and want you to do is hopefully you've gone through the steps, you know how to generate this rectangle. So what I want you to do now is do like a professional geometrician. I want you to set out, we just did the steps. Again, the way you learn this is through repetition. Go back, and now I want you to do a nice, clean, root 2 rectangle. Use soft lines, light lines to get everything that you need set out. And when you have the 4 corners, then go ahead and you can darken it in with your more permanent lines. And while you're doing that, I will read you some interesting quotes here. Well, I'll show you one more. Here's, this is, I forget the name. I visited this mound. It still exists, but if you look up here, you can see that this mound is, Indian mound is framed on a perfect root 2 rectangle. You can see the yellow lines bounding the rectangle. All right, so St. Augustine said, numbers are the thoughts of God. Galileo said mathematics is the alphabet with which God has written the universe. Johannes Kepler said geometry existed before the creation. It is co-eternal with the mind of God. Geometry provided God with a model for the creation. So when we start looking, we just saw a few very simple examples, you know, looking at the earth and its relation to the cosmos, and we find that these numbers that measure the earth are embedded in a lot of the ancient systems that still come down to us today. At the entrance to Plato's Academy, it said, "Let none enter here who are ignorant of geometry." And why was that? Well, a couple of reasons. Number one, if you don't want to get lost in the metaphysical jungle, you want one of the greatest tools or weapons in your arsenal is the ability to think critically. So there's that, and then there's also the knowledge that you can apply this system to the creation of beauty and harmony. And you might just glance up for a second. This is the Zen calligraphy spelling out the word creation, written from right to left, and you'll discover that in your drawings, the most fundamental geometric form is the circle. Then from there, you can derive the equilateral triangle, and then from there you can derive a rectangle or a square. So read from right to left, that is the sequence. Yes?
In masonry, that's the super excellent master.
Sorry?
In masonry, that's the super excellent master degree in the yard.
Yeah, okay. Nice. The super excellent master's degree. In New York, right. Right, in New York, right.
Doesn't everything depend on a foundation of integrity, though?
Well, sure. How could I disagree with that? You know, yeah. What are you asking? Of course, anything worthwhile and good depends on a foundation of integrity. Now, we could think of that structurally. Think of this, a foundation it has to have integrity if it's going to hold up the building, isn't it? A foundation has to have structural integrity or it won't hold up the building that's going to be sitting on the foundation. So I suppose you could apply that equally to a moral code. It starts with a foundation of integrity.
But rocks are changing all the time, on top of rocks.
And what?
Rocks are changing constantly, and you're sitting on rocks.
Okay. We're sitting on rocks. But rocks change really slow relative to the human scale of change, except with, certain exceptions when things speed up over short terms, and then things change very fast for a little while, and that's what we call a catastrophe. So this is what you're going for right here. This is going to test your skills. Draw a nice, beautiful root 2 rectangle. Sorry? A square is a root 1 rectangle. And then the diagonal of the square gives you the root 2 rectangle.
Well, it gives you a root 2 line, but that doesn't turn the square into a rectangle without turning it into a rectangle.
But that's your starting point. You draw the diagonal in, and that gives you the long side of the rectangle.
Okay.
Look at this. Look what's up on the screen. That shows you how to get the root 2 proportions from the diagonal of a square. What was that? This. Back further, this. Oops, well, we don't want to see that. This, how you get the square. Yeah. So all you need, think of this, you just need that right angle, and then the square that you superimpose on that is kind of arbitrary. You just have to mark out on the horizontal side, the vertical side, the same length. Then you use those points to get the fourth corner of your square. And for anybody who does the course, you get handouts with all what you're seeing here with the instructions, and you get the video so that you can do it at your own pace. You can, like I said, repetition is the key to mastering it. So you can go through as many times as you need till you feel like you can do it with, the key is being able to do it without thinking about it. Just, I suppose, like memorizing a poem or playing a song. You know, when I'm learning a new rhythm on the drum, I have to think about it, and I keep doing it over and over again until then I can do it without thinking about it.
Hey, Randall.
Yes.
Can you explain the significance, both esoterically and practically, for squaring the circle?
Well, it's kind of a, okay, well, it's, I suspect that there's a vibrational aspect to it, but symbolically, you know, you look at circles and squares. Squares are a symbol of the material realm. Circles are the spiritual realm. Squares are finite because they're measurable, they're rational. The sides of a square, simply the side of the square to its perimeter is rational 4:1. The circle is irrational. So you have rational, irrational, material, spiritual, finite for the square, infinite for the circle. Because once you have a circle, there's no theoretical starting point or end point. It could be anywhere in the circle, whereas a square, a starting point is going to be one of its corners. So you've got rational, irrational. You've got also the square. You've heard like the four corners of the earth. The square is a symbol for the earth. The circle is a symbol for the heavens. The square, which is angular and is considered usually masculine. The circle and the arcs of a circle are considered feminine. So there's all of these symbolisms that are associated with the figures. And so if you're looking at any kind of symbology and you see squares and circles in there, you can contemplate these ideas associated with them. So each one was, in a sense, a repository of interconnected ideas. In the squaring of the circle, it's about reconciling the irreconcilable. Because here's the thing. You can, for example, you know that if you're given a square, it's a simple matter of drawing four sides, right? And the perimeter is going to be 4 times the length of the side. Well, now draw a circle. What's the relationship of the circumference of a circle to its diameter? Well, it's an irrational number. It's a number that constantly, it goes on forever. It doesn't repeat. It doesn't terminate. It's irrational. So in a circle, you can apply a rational number to the circumference, then the diameter is irrational. Usually you apply a whole number or either an integral value or a real number to the diameter, and then the circumference becomes an irrational number. And so it's well known, one of the problems of geometry has always been to set out geometrically and draw a square and a circle whose circumference is exactly equal to the square. But you can't do it. It's not possible using the methodology of geometry. What you can do, though, is you can approximate it very, very close. And in many of the examples, like the Great Pyramid, is a demonstration of the squaring of the circle. And it approximates the square base of the pyramid, Khufu's pyramid, if you were to take a circle whose circumference was exactly the same as the square perimeter of the base, and you were to expand it by the number we've already learned about, 43,200, that circle that square of the base pyramid, if you turned it into a circle and expanded it 43,200 times, it would give you virtually, almost exactly, the equatorial circumference of the Earth. And I think that was built into it. And that's something will be beyond our scope of what we'll be able to accomplish today, but in the more advanced exercises, we go through that. We break it down very methodically and see how those relations work and how that geometry is built in. It's fundamentally, it's based upon the golden ratio, the divine proportion geometry. Because within that divine proportion is a solution, a very precise but not exact solution to the squaring of the circle property. Exercise, yeah. You've seen that. Where did you see it? I'm curious. Oh, okay. Yeah, I don't know anywhere else where that's been shown. But yeah, it's amazing. 755 feet. And that's the diameter of the circle at Newark. Pardon me? How to get the square? Come up here. Come hither. Come up here, and I'll show you right here. I will give you a one-on-one lesson. So if you go back to the paper, then everybody can see I'm going to draw this again. I'm going to go through the whole sequence of steps. All right. Can I narrate it? Yes. Okay, so I've drawn my baseline. This is the exercise erecting a perpendicular to a given horizontal line. And now I'm going to erect my vertical line like that. Then I'm going to erase, because you all know now how to do this, I'm going to erase all my scaffolding, all my temporary set. Okay, so now this is what you're going for, right? You just want perpendicular. You couldn't do this? Okay, so if I did it again, would you get it, do you think?
You made a point.
Yeah, so I,
put a random point in the middle.
yes, it sounds like you've got it so far. So I do this, and then I'm getting this here. So now I've got, these are my two key points. Project that line right up until it meets the circle. And where that intersects, that gives me my vertical. Now all I got to do is just arbitrarily pick any side length, and I think I've got that there, so I'm going to use it.
Okay,
Transfer it there. Watch careful. Now I'm going to do this. 1, 2, and there's my square.
Thank you.
Think you got it?
I think so. Let me try.
All right. Okay, so if you can see what I've got up here on the paper, hopefully you can see this. I'll darken it in here. Now I'm actually, since I'm going to actually turn this into a root 2 rectangle, I'm not going to draw the four sides of the square. I'm simply going to project the top and the bottom out, and then I'm going to take the diagonal of the square, and it's that diagonal that's going to give me the side of the root 2 rectangle. So there's my diagonal right there. and here. And then what I'm going to do is I'm going to simply transfer that distance to my extended top line and base line, and that is going to give me my root 2 rectangle. So the long side of this rectangle is to its short side. Long side to short side is the same as the diagonal of the square to the side of the square. And there's a whole family of dynamic rectangles, and this is the first most basic one right here. So now, what I'm going to do is we're going to kind of reveal the fractal pattern of the root 2 rectangle. So to do that, now just watch, I'm going to put a diagonal in here like this. Then, now this is where what we've already learned becomes important. We learned how to erect a perpendicular to a line, a given line, through a point not on that line. And I'm going to do that right here below this drawing so that you can see it. I'm going to draw a line, then I'm going to draw a point not on that line, and then I'm going to erect a perpendicular to the given line through that point. So I'm going to do this. I'm going to come around, and I'm going to get 2 points of intersection here and here, and then simply open more than halfway. I think I'll go down here like this and like this. And from that crossing, I've got 2 points now, and I can generate a line like this, and here is my perpendicular. I'm going to do that same thing, but my given line is going to be the diagonal. So you got to watch close to see what I'm going to do. My given line is going to be the diagonal, and my given point is going to be this corner right here. So I'm going to put this at the corner right there. I'm going to make sure that I'm right there with the side of my rectangle, and then I'm going to side of my, what was originally my square, and I'm going to come up here like this. See what I'm doing? I've got that length. I'm coming around this way, and what I'm interested in is where this crosses the diagonal, right here. So that's this point right there. Now, I'm going to do the same thing here, just visualize that this line is this line. So now, I'm going to come here like this, and I'm going to go 1, 2. And then I'm going to draw my perpendicular to the diagonal, and I'm going to stop it right there. And now with that step, I'm beginning to reveal the fractal nature. Because what I've done is I've created a series of triangles, and they're all similar. They're all going to be the same shape. Now, in geometry, we have forms that are identical and forms that are similar. Forms that are identical are the same size and the same shape. If they're merely similar, they're the same shape, but not the same size. So the interesting thing that I've done here, and I'm probably a little off, and the reason I'm getting sloppy up here is because I'm not right over the paper like you can be. But notice what I'm going to do is I'm going to put my compass here at this point where this perpendicular to the diagonal meets the base, and what we're going to see by using our compass, and we can prove this mathematically, but you're going to see that it divides the base into 2 equal parts. It splits it in 2, okay? So now I can take this right here, I can transfer that to the top line, and then I can split it right down the middle this way. And what I've done here now is I've created 2 replicas of the original rectangle. So in other words, this right here, let's do it this way. That's a root 2 rectangle. It's simply the same proportions, it's the same shape, different size, it's flipped 90 degrees. That's a root 2 rectangle. So now I can begin to insert more lines that will reveal the hidden dynamic symmetry within this figure, like this. So what's happening here is I've now created two rectangles that have the proportions of the original, and I can do this. Did you notice how it replicated itself by splitting in two? Almost like it's a metaphor for cell mitosis. The cell is one, it splits into two, and each of those two are now replicas of the original. Now, the two that I've created here, here, and here can be further divided because I've generated, here again, this is the logic of geometry, I've got a crossing point here and a crossing point here, and I can use my straight edge to connect those, and voila, I will now have 1, 2, 3, 4 root 2 rectangles. And by putting in additional diagonals, like this and like this, I get the same thing. I get crossing point here, a crossing point here, and now I can connect those, and I've got 1, 1, 2, 3, 4 small root 2 rectangles. And I can carry this process to infinity, or as fine as my sharp pencil can go, and I will get this self-replicability of the root 2 rectangle. So what has happened here is I have this mathematical relation between the part and the whole. And this was considered to be one of the fundamental keys to harmony, is that there is this intentional relationship between the whole of a composition or a system and the part. So this is where you get this fractal self-similarity or scale invariance. And see, by adding additional diagonals, I can keep going with this process, see? I can do the same thing over here. I can put in a diagonal this way, I can put in a diagonal this way, and then I get these points here and here. That allows me to do this. And I can carry this process to any degree of infinity that I'm capable of drawing. Now, also, the converse is possible. If I want to go larger, I simply extend the two sides like this, and then I will use my compass like this and transfer that here and here. Disregard this. I think you'll be able to hopefully see what I'm doing here. So now I've doubled the size of my root 2 rectangle, and I can put the diagonals in there, and I can do everything here, see? Yeah.
At the very beginning, when you had your bare rectangle, what was the first ratio that you used on the circle?
Okay, when I had the bare rectangle, I put in the diagonal. And I could have done either diagonal, but I chose for consistency to do the lower left to the upper right. Then I used that diagonal, and I erected a perpendicular to that diagonal, which was this line here. I erected a perpendicular that went through that upper left corner. And then I drew that perpendicular down until it intersected the baseline. And where it intersects the baseline, it precisely divides the rectangle into two.
You have to draw a perpendicular to the diagonal.
Yes.
Intersects the upper left corner.
Yes. Now you could do it the other diagonal up to the upper right corner. It doesn't matter, right? All right. Now, I think, don't go back to the computer yet. Okay, so I'm going to show you. Okay, now, yeah, let's go back to the computer now. Okay, there we got it. So you can see the diagonal. Don't worry about the angular measurements for now. But here's basically what you're doing. If you look up here, you'll see I've drawn a whole circle up here so you can see. And then what we've done is we've produced this point there. Then, from there, I've labeled the points, and then I can set that perpendicular. Look at there. See, I'm doing down here below, 1, 2, and that point R is the intersection of those two arcs. The center of those two arcs are A and F. Okay? Then I use my straight edge from B to R, and that allows me to draw that in like that. But really all I want is this. And then once you get this, now you've got the beginning of the dynamic symmetry. So we're going to get a whole collection of similar rectangles in there that all have the same properties because they're the same shapes, right? This sets out, you can see these are the four, just four of them, similar triangles, same shape, different size, establishes the basis for fractal self-similarity. And let's see here. So watch this now. Okay, so now here you're going to see the dynamic nature of this rectangle. So watch carefully. You'll see 1, 2, 3, 4, 5, 6. And again, using the concept of a limit, that spiral, that whirling spiral figure there, just converges on an infinitely small point. But see, what the ancient builders knew and the ancient masters, artists and stuff knew was these points are points, these are the dynamic points within the pattern of the root 2 rectangle. And they knew how to utilize those. And even though an untrained eye won't necessarily identify them, nonetheless it creates something inherent within the composition that is discernible even on an unconscious level. And then those crossing points gives you another root 2 rectangle. And then if we just go through this, you'll see the whole process of subdividing, creating replicas of itself. And you can carry this, and then you can use this to create a template, see? Now, if you're doing a painting and you want to lay it out, and you want to establish it in such a way that those dynamic points are somehow emphasized in the composition. And you can carry this to any degree you need it. So then from the root 2, out of the root 2 is born the next dynamic rectangle in the family, which is the root 3 rectangle. And it's actually produced the same way you create the root 2 out of the square, you create the root 3 is born out of the root 2. And then that gives you a whole series of interesting fractal properties, which are similar but different. And in the root 3 rectangle, you'll see that the perpendicular to the diagonal divides the base into 1/3, like this. And then you can see there's a whole similarities within that. And again, you can create a template. So this gives you the root 3 harmonic grid. And I'm just showing, right? adding some color in there just to show you some of the patterns that are inherent within it. All based on a root 2 geometry. And look what else is hiding, I'm sorry, root 3 geometry. Look what's hiding in the root 3 geometry. There's your hexagon. Oh yeah, primarily in crystal and structure. So that's your root 3 harmonic grid. And you can see, like we just drew our Star of David, that's hiding in the root 3 geometry. And that also gives us the so-called flower of life. Which is hidden within that root 3 dynamic symmetry. So, go ahead and play. Draw a root 2 rectangle, start dividing it up, and just see what comes. Now see, if we were doing this a regular retreat, you would be getting out your colored pencils, putting on your little propeller beanie, and going crazy. And in the weekend workshops, we are going to be providing propeller beanies for everyone. Oh, let's see.
I'm like an eighth of an inch off from the center.
He's an eighth of an inch off. This is totally unacceptable. Well, let's see here. How close are you to a perfect square? Well, that's good. Your square is good. Okay. Let's see your diagonal. Well, that's good.
Yeah, rectangle, right? I think.
Yeah, you've got it there. So let's see. Then what I did, the way I usually do it, is I'll take this. You got that, okay. Then you'll take this here. That looks good. Slightly off, but it's, well, here's the test, the ultimate test. Let's see. What did you do? This isn't funny. This is serious. He's off by an eighth of an inch.
This is like unholy geometry.
I'm not sure what you've done, actually. But, you know, your compass might have slipped, but I just went through it. It should have, but that's okay for now. So what I'm going to suggest you do is, ordinarily I wouldn't allow you to cheat, but given the time constraints, you can cheat. So basically you're going right there. That's what you want, is the middle, right? So let's see if that's the middle. That's pretty close. So now you can put that up there. Let's double check. Yeah, that's good. Close enough. So then you would, now you can draw this like this down here, and then I would go ahead and erase this. Now you don't need that anymore. And now you can, start adding your diagonal. So if you add a diagonal like this. Really? We're already? Oh my God. Okay, so then this.
Autograph this one when we're done.
Sure.
I was kidding, but yeah, that's great. Now I'm going to keep it.
Cosmic. What is this? Cosmic Summit. Summit 2025. There you go. Now you know where to go from here, right? And so you've got that will give you.
Thank you.
I've just been informed we've already gone through, it's already almost 4:30. Time flies when you're having fun. So if you want to really get into this, you can go to HowTube. I've got a whole weekend of stuff recorded. We have the overhead camera. And if you sign up for that and let me know, we're going to mail out, I've got written instructions that walks you through the basic steps, because we've barely gotten into this today. So you can get that and then play at home. And coming with that, if you want, we already have a bundled cool tote bag with everything in it you need, including the calculator and the colored pens, colored pencils, a nice steel straight edge, which works really slick, the 2 sizes of the compass, including the custom-made compass that we developed, because I couldn't find anything really suitable on the market. So we kind of came up with one, and that's what you're using. Oh, and by the way, let's see. Beckett, are you in here? What is the deal? Is it people have an option to purchase the compass? What? Oh, you get to keep the compasses. Okay.
Yes, you get to keep the compasses.
For the tuition, is that the deal?
Yeah, we'll sort it out.
Yeah.
I've been trying to construct that stuff. I think it's really cool looking. I don't know what I think about the philosophy of it. I mean, he seems like a horrible person to me, but the constructions are so...
Oh.
They're the way that they grow is pretty organic.
Okay.
What do you think about it? Should I waste my time?
I've read a few things of his years ago. I couldn't really advise you, I don't think. Yeah, I'm not. I actually have a little book on his geometry that I may have worked through years. Oh no.
Well, it's non-Euclid. God is at the infinitely distant point where parallel lines meet.
Okay. Oh,
I
okay.
just like the drawing.
Oh, okay. Huh. All right.
I'm just saying. Thank you.
You're welcome. So, let's see here. If you want to look up here for a second, I'll just give you an example of the kind of things we get into in the upper levels. So this is 2 squares, and the corners of these squares would coincide with the corners of an octagon. And from there, we create an octalpha. I think this is up on the screen. And watch this. Just take a moment and watch this. I'm going to go through this because this is a cool thing to end with. You see I've inscribed a circle within this interior octagon. And then by extending the lines out, I use, it's geometric logic. I can create an extended pattern like this, which then allows me to draw additional circles like this. And every step is built upon the previous step. And so what I end up with is this pattern here. Then I walk you gently through the mathematical derivation of these ratios. But the key here, if you look at the ratio of AD, which is right here, the radius of this outer red circle, to AB, the radius of the inner circle, that radius equals the ratio equals 1.83, okay? And this is just one example. There are many examples like this that we could get into. If you see here now, I've abstracted just those two circles, AD and AB right here, with the ratio, size ratio of 1.83. And then I'm tilting it down obliquely, and then you'll see what I've got here. So you've got the Sun to Saturn mean distance, the Sun to Jupiter mean distance, 8.886.7 Sun to Saturn, 483.7 million miles Sun to Jupiter, and the ratio is 1.83. So there's a hidden geometry in this solar system that we inhabit. And without that geometry being precisely what it is, we couldn't exist. So this is the kind of things we will explore in the more advanced studies. And the way you learn this is in the classes, I actually go through this exercise and we draw it, right? And then there's also going to be a digital component as well, digital exercises that you can do in your computer, depending on what software you've got. But most of the softwares, I use a CAD system, and it's very similar to other things that I've seen. Other drawing systems and, design, Photoshop and so on has the same functionality. So if you're familiar with that, you should be able to adapt the techniques quite readily. And it's a lot of fun to do this in the computer. All right, so is that it? I'm seeing a thumbs up from Beckett. So we're done. I was hoping we could have got into a lot more because there's we've basically just taken a peek inside this extraordinary realm of geometry. But hopefully some of you will decide to go further into it. Well, you can go to HowTube now and you can download like 10 hours worth. It'll take you through everything we've done today plus a lot more. Pardon me? HowTube. Yes, here, I'll give you, would you give her this card? Well, I got to work on it. They're not ready yet. I'm hoping to have the intermediate course by the end of the summer, like maybe by the end of August, ready to download. Okay.